In Lecture 26, I'm going to continue to examine the electronic properties of materials and focus on what many commentators think are the defining materials of our modern age, semiconductors. The great principle for this lecture is that modern electronics rely on semiconductors, which control the flow of electrons. My basic outline is first to look at the structure and the bonding of silicon. Silicon is the essential element of modern semiconductors. And we're going to see that there are two distinctive types of semiconductors, the N-type and the P-type. Then we're going to look in more detail about how semiconductor devices work in all sorts of modern electronic appliances. Finally, I'm going to introduce the idea of electronic information and explore the workings of the modern electronic computer. In the last lecture, we surveyed many of the properties of materials. And I examined 5 of those properties and showed that each of them was in some way related to the atoms and how those atoms are bonded together. For example, we talked about the strength of materials. We had compressive strength. When you squeeze a material, how strong is it? We have tensile strength. When you pull on a material, how strong is it? For example, a rope, a chain of atoms that are linked strongly together, is a very strong material under tension. And then we had shear strength, the twisting of a material. And only if you had a rigid cross-linking in 3 dimension of bonds could you have material that was strong under twisting or shear. I also talked about thermal expansion, the fact that many materials expand when they're heated because the atoms, as they move faster and faster, bump into each other. But a few materials with very, very strong bonds, actually contract when they're heated because strong bonds link together, and as the angles get larger and larger, the atoms get closer together. We talked about stickiness, the fact that there are glues and tapes and adhesives that want to bond to other materials, so they're sticky, but we also search for materials that are non-sticky, materials that have surfaces that to all the world look like inert gases that don't bond to anything. Magnetic properties are another example, where individual atoms have electrons in orbit, tiny dipole magnets like an electromagnet. And if all those atoms are aligned together, the bulk properties of the material are also magnetic, and that's how permanent magnets form. And finally, I talked about electrical conductivity, the ability of some materials for easy flow of electrons, as in metals, and other materials, insulators, in which electrons won't flow even under a strong electrical voltage. Well, as we saw in the last lecture, every electric circuit requires both conductors that carry electricity and insulators that resist the flow. But you know, if the only materials we had were conductors and insulators, the world of electronics would be very limited indeed. We could, of course, manufacture many useful devices. For example, we could make electromagnets and electric motors. This, for example, is a motor from a coffee grinder, so you could grind your coffee with insulators and conductors. We could also generate electricity with electric generators, like this alternator from a car. We'd be able to light our homes. We'd be able to heat our homes with electric current. But many of the modern marvels of the electronic age, computers, CD players, so many of the electronics we use in day-to-day life wouldn't be possible without semiconductors. Let's begin by seeing how these critical semiconductor materials work. First of all, you should know that semiconductors conduct electricity, but not very well. Most modern semiconductors begin with a crystal of the element silicon. That's element 14 on the periodic table. Now, silicon, when it's electrically neutral, has 14 protons and 14 electrons. So it has a half-filled outer shell. 4 of the 8 possible electrons are present in the third shell. So silicon's strategy, just like carbon, which is above it in the periodic table, is to find 4 more atoms. In a silicon crystal, then, each silicon shares 4 electrons with 4 neighboring silicon atoms. So every atom sees the full complement of 18 electrons. Now, this situation is very much like the covalent bonding of carbon, which lies just above silicon, as I said, in the periodic table. Silicon is a very poor conductor of electricity. Since all the electrons are locally shared, since each silicon sees those 18 electrons, there's not much incentive for an electron to go traveling off as an electric current. But I want you to think about what happens now if you substitute an atom of phosphorus. Look at the periodic table. That's element 15. Phosphorus now, instead of 14 electrons, has 15 electrons. That's one more than you need to give a filled shell in the silicon crystal. So this extra electron becomes delocalized, just like electrons in metal. What you do is add a small fraction of phosphorus impurity to a silicon crystal, no more than about 1 atom in a million. So engineers add a controlled number of these negatively charged electrons, effectively, to a silicon crystal. And the result is an N-type semiconductor. That's a semiconductor with a few mobile negative charges, a few electrons. By the way, that minor impurity, the phosphorus, is called a dopant. And this process is called doping of the silicon crystal. Now, apply the same logic to a silicon crystal in which a single atom of aluminum, element 13, substitutes for a silicon atom. In the periodic table, aluminum is right next door to silicon, element 13. Well, here with 13 electrons, including 3 electrons in the outer shell, you have one too few electrons. There's essentially a missing electron in this silicon crystal now. A missing electron is called a hole in the terminology of electronics. And a hole is essentially the absence of an electron. It carries a positive charge. By adding a small fraction of aluminum atoms to a silicon crystal, then, you're adding a controlled number of positively charged holes which can move around the crystal. And the result is a p-type semiconductor. Now, one important point, N and p-type semiconductors in and of themselves alone are just lousy conductors of electricity. They don't really have any significant use by themselves. They only have about 1 in a million atoms in these cases that are contributing a mobile charge carrier to carry electricity. So they have no special use in electrical circuits. In order to think about N and p-type semiconductors, I want to give you an analogy. Think about a huge, crowded parking lot, just say on the 24th of December, just before Christmas, when everybody's out shopping, looking for a place to park to visit the mall. Now, N-type semiconductors are very analogous to a parking lot that's completely full with a few extra cars driving back and forth in the rows trying to find a parking place. Those cars just keep moving about. They're like the electrons that can't seem to find a parking place in an N-type semiconductor. A p-type semiconductor with holes is a situation where you have a very crowded parking lot, but there may be just a few empty parking places. And now you have to imagine that the shoppers, eager to get as close as possible to the store they want to visit, are constantly sitting in their cars, waiting to dash out of one place to get to a place that's slightly closer to the store they want to shop in. So, individual cars darting around, but you can model that mathematically more easily, not as cars moving, but as holes moving. Indeed, when traffic engineers model a traffic jam on an interstate, they do exactly that. You could either keep track of the thousands of cars that are creeping along in one direction, but mathematically it's easier to keep track of the few holes that open up and move backwards through the traffic jam. Now, from a materials fabrication point of view, these N and p-type semiconductors are quite remarkable. Most metals, most insulators, and other materials in our world are manufactured in bulk, in big vats or in big refineries and so forth, these things that hold large amounts of material, and you manufacture large quantities of material that have exactly the same properties. But semiconductors are manufactured atom by atom under exquisitely controlled conditions. You have high-tech, ultra-clean laboratories. You have engineers wearing clean suits from head to toe. And you have vacuum chambers where various quantities of atoms are deposited, sputtered off one by one, controlled amounts of phosphorus and aluminum being added to the silicon. Well, now that we understand the bonding and the properties of these individual chunks of N and p-type semiconductors, we can focus on how they work in electronic devices. As I mentioned before, a single piece of N or of p-type semiconductor material is just a lousy conductor of electricity. the magic begins when you put two or more of these pieces of semiconductor material together, join them physically into a single device. The simplest semiconductor device is called a diode, and it's simply a piece of N-type material attached to a piece of P-type material with two wires. Diodes are extremely common in modern electronics. They're very small. They're made of a tiny piece of silicon with an N-type at one end, a P-type at the other end, and two wires coming out of the ends. Now, think about what happens in a situation where you have this sort of arrangement of semiconductor materials. If electric current flows into the negative side of a diode, it wants to flow right on through to the positive side because negative electrons are attracted to the positive end. In fact, the resistance is almost zero in this direction. But if you have electrons flowing into the positive end, they stop dead because negative electrons don't want to go towards the negative side of the diode. And the resistance in that direction is almost infinite. What you have then is a one-way valve for electricity. And there's no simple combination of conductors and insulators that can accomplish that. Indeed, the only way you can do it with conductors and insulator is to form a very expensive and complicated vacuum tube, a rectifier tube. Rectifier tubes have a very hot filament at one end, and they have a very large voltage, several hundred volts, across two plates. The filament is the negative side, and the other end, the cathode, is the positive side. And by boiling electrons off the filament, you can actually get the electrons to go from the negative side to the positive side. But these are large objects, they're hot objects, they take up a lot of space, and there's no way you could have, for example, a transistor radio that you carry along with you with a diode made of a glass tube. When you plug an electronic appliance into the wall, indeed the first device that the electricity sees is going to be a diode. And that's because most electronic devices can't use the alternating current that comes out of your wall. Electronic devices need direct current. So if you ever dismantle an old TV or a radio, what you're likely going to find is that the electricity comes in, the power comes in with the two wires, and the first object it hits inside that device is a diode. This is true of almost all electronic devices. Now, if you can imagine what this looks like, you can think of the current coming in to the diode as having a kind of wave-like character going back and forth, sloshing back and forth. When it comes out of the diode at the other end, you just have a series of pulses of electrons going in the same direction. Now, those pulses aren't a very good way to control electricity in a device, so you need yet another electronic device, this called a capacitor or a condenser. And a capacitor or a condenser acts like, for all the world, like a miniature rechargeable battery that recharges very quickly. You pump electrons into this device, it charges up, and out the other end flows a direct current. So therefore, if you have most electronic devices these days, after the current comes in and sees the diode, the next thing it sees is a capacitor. And the capacitor changes AC into DC current. Well, that's just the beginning of what semiconductor devices can do. The next step is to make a three-layer sandwich. And a three-layer sandwich of semiconductor material is called a transistor. Transistors can be NPN, or they can be PNP. The transistor was invented at the AT&T Bell Laboratories in New Jersey shortly after World War II as part of what was then a great boom in industry-sponsored basic research. I just should say parenthetically that I'm very sad to see that this level of industry support for basic research has dropped way back in the United States these days. And that discoveries like the transistor are less likely to be made in basic industry these days, I think. The three Bell Lab scientists, John Bardeen, Walter Brattain, and William Shockley, shared the 1956 Nobel Prize in Physics for this great invention. By the 1970s, transistors had virtually replaced the vacuum tube in all routine applications. You may remember, for example, that was about the time that you could get battery-operated transistor radios and carry them to the beach with you. What a revolution in the way we listen to music. Well, the transistor has many, many advantages. One of them is its extremely small size. Some of them are microscopic. They're only about the size of the head of a pin. And even the large power transistors are quite small. These transistors replaced vacuum tubes, often called triodes. And the vacuum tubes were much larger. They used 1,000 times more power. They generated lots of heat. They were likely to burn out. They were expensive. This is a revolution in electronics that really changed the way you could use electricity and change the kinds of appliances that everybody could have in their homes. Transistors now find all sorts of use in modern electronics, especially as amplifiers and as logic circuits. The principal use of transistors is as an amplifier. It takes a weak variation in power or in voltage coming in and amplifies it so that the output is a very strong variation in power or voltage. This capability is absolutely essential in things like speakers, which take a small input signal and amplify it into a large sound, in radios, where you amplify a weak radio signal that's coming in, and so forth. You can also imagine how a transistor works as a logic device. For example, an NPN transistor, you can think of these as having two input regions, the N regions as being labeled A and B, the output region being labeled C. And just like two little diodes connected together, if A, if current flows into A, or B, if current flows into B, then current will flow out of C. So we have the logic device, if A or B, then C. Well, the heart of many modern appliances is the microchip. The microchip is an integrated circuit. This is a single semiconductor device that may incorporate thousands and thousands of transistor-like regions. Microchips are tiny. It's amazing how many different N and P-type regions can be contained in one of these small devices. These microchips are deposited layer by layer in vacuum chambers. And as successive layers form, different masks control the amount of N and P-type regions that are deposited. Now, microchips are used to control the application of almost all modern electronic devices. And you may have seen some of the old wonderful circuit boards that contain tens or hundreds of these microchips. I have preserved some of these old circuit boards in my own collection just because they're so beautiful. I have, for example, in my collection a circuit board that controlled an old printer output and input, and there are many microchips that line this device. For the final third of this lecture, I'd like to consider the nature of electronic information and the concept behind the great information technology of our time, which is, of course, the electronic computer. A computer is a machine that processes information. And all modern computers rely on these integrated circuits composed of semiconductor materials. These semiconductors help to store information. They help to manipulate the information. They make information technology possible. Think a bit more about what we mean by information. Now, all sorts of sights, all kinds of sounds, photographs, music, words, numbers, these can all be represented as information that can be stored and transferred, modified, manipulated in various ways by an electronic computer. This is because all these different kinds of information can be converted into binary digits or bits. Now, a bit is just one of two states. It's an object that has either an on or an off, a yes or a no, plus or minus, black and white. And binary codes have been used for a long time. For example, Morse code, the old Morse code that was used by telegraph operators, used pulses that were either long or short. And this sequence of long and short pulses, it could have just as easily have been zeros and ones, are sufficient to communicate any amount of information. My father was an amateur radio operator, and he was incredibly proficient at Morse code. He could type something like 50 words a minute with Morse code, so fast you could barely hear the short and the long pulses, but this became a very effective means of communication. Indeed, any kind of information can be reduced to bits. Let's think about how to reduce the 10 digits from 0 to 9 into binary, for example, just as an example of how one can do this. Now, first, you have to think about the places of the binary number. In binary, imagine 4 decimal places, and the first place represents 1. If you have a 1 in that position, you add 1 to the total. If you have a 0, it's just 0. The second place represents the 2's column. So if there's a 1 in the 2's column, you add 2 to your number. If there's a 0, it's 0. The third decimal place is 2 squared, or 4. And the fourth decimal place is 2 cubed, or 8. So the 4 places are 1, 2, 4, and 8. In this sort of binary number, then, a 1 is represented by 0, 0, 0, 1. A 2 is represented by 0, 0, 1, 0. And a 4 would be represented by 0, 1, 0, 0. And then if you have an odd number, for example, 5, well, 5 is equal to 4 plus 1, so it would be 0, 1, 0, 1, and so forth. For those of you listening on audio tape, it will really help to look at your booklet at this point, because there's a list of the binary numbers expressed this way. Now you can imagine other 4-bit combinations that could represent decimal points, or addition, multiplication, and so forth. So you could do any mathematical operation just using binary codes. You could also represent the 26 letters of the alphabet in this way. But here, you'd have to have more than 4 places. You'd have to at least go to 5 places, because there are 26 letters, and there are only 16 combinations with the first 4 places. So you could, for example, use a 5-digit sequence, and entire libraries could be reduced in this way just to a binary code. By the way, in many computers, they use an 8-digit sequence that's called a byte. Now, illustrations make a particularly interesting case of how you can digitize information. Imagine your favorite photograph, and how in the world could you reduce that to a bunch of numbers? Well, here's how they do it. They're converted to a large number of what are called pixels. And pixels are individual squares of information, each square containing information about color and intensity. Now, in a typical modern video in North America, you have several hundred rows, each with several hundred pixels. Indeed, TV these days is 525 rows, each with 525 pixels. That gives you a total of 275,000 pixels in each screen. They're talking about high-density TV or new kinds of high-resolution video images that would have even more information than that. But 275,000 pixels is a lot. Now, each of those pixels has to have information on red, how much red is there, how much green is there, and how much blue. And the way it's done in modern technology is to have 10 bits of information for each of those 3 colors, or 30 bits of information for every pixel. If you multiply that out, that's 30 times 275,000, or 8 million bits for every single screen on your TV. This is the point where the brain has to take over, because the brain doesn't see lots of individual squares. It integrates that and sees one smooth, continuous image. Indeed, the brain is amazing this way. It can also take a whole sequence of individual images, separate still photographs, if you will, and it can see them as motion if they blend continuously from one to the other. But all of this information, if you take a magnifying glass and look closely at your TV screen, you'll see all this information is contained in pixels. Now, computers are designed to store and to process numerical information. Typical computers store most of their memory, and that's typically billions of bits on magnetic storage devices. On each of these devices, you have small magnetic areas, and the way you store the bit is it's either north-oriented up or north-oriented down. 0 or 1, yes, no. Now, in the old days, when I started working on computers, we used magnetic tape, and you had tape that was coated with magnetic material, usually an iron oxide. And each of these little grains could be oriented magnetic north or magnetic south. Today we have computer disks and diskettes, hard drives, and so forth. They too use magnetic storage by having bits oriented north and south. If you ever have a defective diskette, you might want to break it open sometime and look inside and see that magnetic material. Computations in a computer are carried out in the central processing unit, that's called the CPU, which typically has one or more integrated circuits made of silicon-based semiconductors. And you've heard of the trade names of some of these famous chips, I'm sure. Now, when I began using big computers in the 1970s at MIT, I had to visit a huge central building that had one giant room with lots of air conditioners and just a giant machine. It turns out that giant machine had significantly less power than my laptop these days, so things have come a long way thanks to the impressive reduction in the size of semiconductor devices. Okay, before leaving this subject of materials and their properties, I'd like to end with a general observation. I think it's obvious that new materials change our lives, and it's often changing us in subtle and unnoticed ways. This is very different from the abstract discoveries of astronomy, which are trumpeted in the newspapers, of particle physics that somehow make the headlines in the various papers around the country. We hear about medical advances, advances in biology. We hear about earthquakes and volcanoes. But when's the last time you saw a newspaper headline saying a new variety of semiconductor has been found, or something of that sort? And that's because, unlike these abstract discoveries, the great inventions of material age really occur without fanfare. I want you to imagine yourself back to the early years of the American Republic, 200 years ago. Now, what materials did people have available then? The artisans at the time would have had just a handful of materials. They had stone, they had wood, they had glass, they had a few types of metals and a few types of alloys to work with. They had some natural fibers. They could make cloth, they could make paper, they could make rope using natural fibers. No polymers, no plastics back then. They had very few kinds of paints, only a few kinds of glues and dyes, lubricants. I was astonished to learn in that period there was really no good oil-based, brilliant yellow or orange pigments for painting. And so painters were limited in that way. Many of today's commonest materials that we take absolutely for granted were unknown in 1800. There was no rubber, there was no plastic, there was no latex paint, there were no epoxy glues. There was no aluminum. Aluminum had not been extracted yet. Steel was an extremely rare and expensive alloy. And of course, there were no composites like plywood or reinforced concrete. Today, by contrast, you can buy many thousands of different specialized materials. Some of them, like plastics, are so commonplace as to go virtually unnoticed, and yet these are remarkable high-tech materials. Other of these materials, like semiconductors and superconductors, are always hidden away from view in places we never see. We buy a computer, it's filled with semiconductor materials, but you never see those materials. You take them for granted. And still other materials, like the synthetic diamonds, find use in industry far away from the consumer. This leads to cheaper cars, much faster eyeglass preparation, quieter, less disruptive repairs of road surfaces and so forth. But how many times do you really look at those things and say, ah, diamonds? They're hidden from view. They're several steps removed from our environment. So new materials in this context are usually undramatic, and they make very subtle appearances by their physical presence, but they dramatically transform society. Step by step, year by year, our lives get better and richer as a result of new materials. Well, in summary, silicon-based semiconductors are engineered to have a few extra electrons, that's the negative type, or a few positive holes, that's the positive type. So we have N-type and P-type semiconductors. While they make very poor conductors by themselves, when they're combined in devices such as the diode or the transistor, electrons can be controlled with exquisite precision. The modern electronic computer makes use of semiconductors to store and manipulate various kinds of electronic information. And in the next lecture, we're going to continue this theme of atomic scale behavior. But we're going to turn our focus to the enigmatic behavior of the atom's nucleus.